Hello everyone, welcome back to Electronics 1. We've spent a fair bit of time talking about BJTs, how they work. Most recently we've talked about biasing BJTs to a specific operating point. But ultimately what we're interested in is using a BJT or transistor as an amplifier. And today we're going to start looking at different amplifier configurations using BJTs and look at some small signal models for those BJTs, since we'll now be moving to the small signal realm, much like we did with our diodes. We biased a diode to a specific operating point, and then we could consider the small signal operation as small perturbations around that operating point. So we're going to start by looking at common emitter amplifiers. As the name suggests, they are amplifiers where the emitter is common to the input and output. The input is applied to the base, the output is taken from the collector. Okay, so just like our diodes that are small signal behaviors modeled by this idea of having small perturbations around an operating point that we called Q, and we can look at BJTs in the same way. So again, we'll remember that for our diodes, if we looked at the diode characteristic and we biased the diode to a specific operating point. Actually, let's go with a different color here. We threw some large signal, application of large signal or DC signal. We biased the diode to operate at some operating point defined by the DC applied voltage and the resulting DC diode current. Well, the same concept applies to BJTs. We can, through the application of a base to emitter voltage, we can bias the diode to a specific operating point. Again, we will call that operating point Q, where there is a specific collector current for an applied base to emitter voltage. And just like with the the diode, we said the total diode current is a function of our saturation current and our total diode voltage, that being the both the large signal and the small signal component. Well, the same is true for our total collector current. In a BJT, it's a function of our saturation current and times e to the VBE over VT. And you'll note here that there's no ideal D factor. We assume that the ideal D factor for a BJT is 1. Okay? And you might recall that we went through some derivations to show that for a diode we could define small perturbations, or their small signal, as signals that were less than NVT, our ideal D factor, times our thermal voltage. Oops, less than this. Okay, so as long as our voltages, diode voltages, were less than this, we could treat those as small signals, and we can assume linear operation. Okay, so same kind of idea for a BJT. As n is equal to 1, then it's a little bit simpler in that our base to emitter voltage simply less than our when it's less than our thermal voltage, which we know is approximately 25 millivolts, at least at room temperature. Then for values of VBE less than that, we can treat those as small signals, and we can treat the operation as linear rather than having to deal with the exponential behavior that is defined by our equations up here above. And we remember that this was based on a Taylor series expansion that we worked through back in our diodes, so we won't bother going through that again. Okay, and just to draw a figure from the textbook, so this is figure 7.22 from Cedric Smith, that shows this this small signal component applied as VBE, causing small fluctuations around our operating point Q. Okay, and this operating point or bias point is set or determined by our large signal, or our bias network that we've been analyzing so far. That'll set some bias point or some specific value of collector current. Remember that the collector current is related to our base current as beta, or common emitter current gain, times our base current. Okay, and we see as a result of these small signals applied to the input, we get a large signal occurring at the output, and that's the amplification effect that we are hoping to achieve from our BJT, right? Small changes in VBE result in large changes in our collector current around our operating point. Okay, just be clear that this is from Cedric Smith here. Okay, the other thing you might note, just like in the case of our diodes, that there is just take some of these things away, there is a slope or a transconductance that is associated with our operating point. So this is shown on the graph as a line drawn tangential to our BJT characteristic at the operating point. Okay, and from that we can come up with a transconductance parameter, just like we did with our diodes. Transconductor conductance parameter GM. So we see that shown here as defined by this slope at the operating point, and that transconductance parameter, much like in the case of the diode, is defined as the so if we go through a small signal linearization, we can show that the transconductance parameter is a function of our technically are changes in IC at due to VBE, okay, due to changes in VBE. Again, we eventually worked our way down to show that transconductance parameter could be simply defined as IC divided by VBE, those through a small signal linearization. And if you look back at our analysis of the transconductance parameter, when we were looking at diodes, we worked our way through to show that this transconductance term at our operating point can be found by the collector current, or in the case of the diode, it was the diode current at our bias point, so that large signal current divided by our thermal voltage. Okay, again, where this is based on our bias point. And if you looking at the characteristics shown here, that makes pretty good sense, right? Depending on where our collector current falls here on this curve determines what the slope is at that given point, what our transconductance is at a given point. Okay, so this is a very important parameter that we are going to use in our small signal models. So from our bias conditions, we set a small signal parameter around which the device is operating from a small signal perspective. Okay, the beauty of this is that at this point of operation, at this operating point Q, at the bias point, we can treat our operation as linear. Okay, just like we did with the diode, we don't have to consider the exponential nature of the diode anymore, because for small perturbations, right, as we defined up a bit above here, for small perturbations, the operation around that range of perturbations we can assume to be linear. Okay, so again, this is a significant discovery here, this transconductance parameter for our BJTs, and this can be calculated for all BJTs in the same way, this transconductance term. Okay, how does this help us? Well, this leads us to some BJT models that are much simpler than in the small signal realm as compared to the large signal or DC bias models. So going back to our T models, we looked at back a few lectures ago, we developed a model for our BJT that looked like this, where we represented the junction between the base to emitter as a diode, and we represented that collector junction as a controlled current source, right? And based on the applied VBE here, we would get a certain amount of collector current and as well emitter current. And we'll recall that the our saturation current in this model is defined based on our collector current. So the saturation current of this diode that's actually in the emitter circuit is going to be scaled by alpha, that quantity that links our emitter current and our collector current. Okay, so this is our large signal model. We dealt with this model in a fairly simplistic sense because we tended to just treat this diode as a constant with a constant voltage drop model when we're doing our large signal analysis of our BJTs. So that greatly simplified our analysis, but if we want it to be precise, the analysis is in fact exponential in nature and is much more complicated, but we've tended to be happy with just using this constant voltage drop model for our analysis, and we'll continue to do that. But when it comes to the small signal model, again, much like the case of the diode, we can replace this exponential diode behavior now with simply a linear term or linear relationship, which is represented as a resistance. And we'll see in a second here how this resistance relates to this transconductance parameter that we discovered up above here. Okay, so much simpler model in the small signal realm, and allows for much simpler analysis of behavior of the circuit in the small signal realm. Okay. I guess technically this is IC here, and this constant controlled current source is also IC. Okay, so again, this large signal model, as we know, calculating the operating point. Let's use the emitter current as an example. Calculating the emitter current is not trivial, right? It involves this exponential, and we've seen the challenges in dealing with this nonlinear model. Okay, so large signal, so our model is nonlinear. As shown in this expression for emitter current, but our small signal model is linear, and we can treat it as linear as long as our small signals adhere to what we've defined here earlier. The VBE values are less than our thermal voltage, similar to what we did for our diodes before. Okay, so looking at our T model, our small signal T model, you'll note that we have a voltage of VBE across this resistance, which is known as our intrinsic emitter resistance. Okay, we'll give this a name, I guess, here. This is our intrinsic emitter resistance. And so the analysis of this circuit becomes quite straightforward. Our emitter current in that circuit can be calculated simply as our base to emitter voltage over our intrinsic emitter resistance. Okay, simple Ohm's law. that intrinsic emitter resistance, if we dig into it and we just rearrange this equation, you can see that the intrinsic emitter resistance is our small signal base to emitter voltage divided by our small signal emitter current. Okay, and we know that our emitter current is equal to our collector current divided by alpha. Okay, so rearranging here, we show that our intrinsic emitter resistance is equal to alpha times VBE over IC, our base to emitter voltage divided by our collector current. Now, this term here should look familiar. We saw up here that our transconductance parameter, it was equal to our small signal collector current divided by our small signal base to emitter voltage. Okay, so we can this is in fact equal to one over GM. So substituting that in, we can show that our intrinsic emitter resistance is in fact equal to alpha over our transconductance parameter. Okay, this is another small signal parameter of significance, and well, and as we see that it's used in our small signal T model. Okay, so RE, which is often referred to as intrinsic emitter resistance, can be thought of as the resistance of the forward biased base to emitter diode. Okay, again, just like we did with our diodes, we come up with a small signal resistance of the diode, and that we were able to use for small perturbations to the diode voltage and model it as purely a resistance. So we're doing that same thing here. Just a note here, this is often handy to remember that if our collector current is equal to 1 milliamp, so going up here and referring to this transconductance term, right? So remember that our transconductance is equal to this. So if this is 1 milliamp divided by 25 millivolts, and we substitute that in for our E here, which we said is alpha over GM. If we put this 1/25th, well, it's actually Siemens. If we put that value in for our transconductance, we're going to get, and we know that alpha is approximately equal to 1. We're going to get an intrinsic emitter resistance of approximately 25 ohms. So that just gives you a ballpark value of what we might expect for intrinsic emitter resistance, kind of at a pretty typical operating point for a BJT. Okay, so that's our T model and the associated intrinsic emitter resistance that is in that T model. So let's now look at our pi model. So we looked at pi model for large signals in a previous lecture, and you might recall that the pi model looked like this. Where this is our base, our emitter was common to both the input and the output, and here's the collector. Here we have this controlled current source again that is IC. We have now a base current that is a function of our applied base to emitter voltage. And now the diode in this model, you'll remember, has a saturation current scaled by beta, right? Because again, our saturation current in these models is based on our collector current, and since our current through this diode is base current, well, then the saturation current has to be scaled by the relationship between the base current and the collector current, so it's scaled by a factor of beta. Okay, so this is our large signal pi model. So we can now develop a small signal model that's linear for small signal analysis using the pi model. Okay, so much like our T model, we are simply going to replace the exponential diode in the circuit with a linear element, that being a resistor. And this resistor is known is R pi, where R pi is that small signal resistance from the base to the emitter. And just label these, and again, of course, the controlled current source represents our small signal collector current in response to our small signal base to emitter voltage. Okay, so this is our small signal model. And large signal model, we know that the base current is exponentially related to the base to emitter voltage. Okay, and we could show this as rearranging this. We could show it as a function of the collector current, if we want it. Okay, but for our small signal model, our base current is again a linear relationship we can calculate simply using Ohm's law. Let me label the base current on here. So that base current is simply equal to the base to emitter voltage divided by that base resistance R pi. Okay, just like we did in the last case, I can rearrange this in terms of R pi, showing that it's equal to VBE over IB. And again, I can, just like the last example, we can write IB in terms of our collector current. And here we see that when I rearrange this, my R pi is equal to beta times VBE over IC, which is, here is this term again, that's equal to 1 over my transconductance parameter. So I can therefore define R pi as being beta divided by my transconductance parameter. Okay, so here is a third important small signal parameter in our that will be used in our small signal analysis, at least if we're using a pi model. I should be careful here, or should point out, I guess, that this pi model is often actually referred to as the hybrid pi model. Okay. It's also worth noting that with a little bit of manipulation here, you can show that R pi is equal to beta plus 1 times RE. Shouldn't be super surprising that the resistance in this model, so the resistance in the pi model is the resistance associated with the current in the base, whereas the RE is associated with the current in the emitter, and that current in the emitter is beta plus 1 times larger than the current in the base. So when we model the resistance in the pi model, we have to model that resistance as beta plus 1 times larger to have that scaled impact with the smaller base current. Okay, let's just do a really quick example of finding these parameters, and this is often what is one of our first steps in doing our small signal analysis, is that we have to first do our large signal analysis and come up with an operating point. I'm going to assume that that's already been done here. So we have a BJT that has a common emitter current gain of 200 and has again, through some large signal analysis, it's discovered it has a collector current of 5 milliamps. Okay, and we might also note that from the data sheet of this device that it has an early voltage of 100 volts, let's say. Okay, so we want to find our small signal parameters to be used in our small signal models, whether that's the hybrid pi model or the T model. So we want our values for our transconductance parameter, RE, R pi, and our output resistance. That's a function of our early voltage. Okay, so the first thing we always need to start with is calculating our transconductance parameter, because the R pi and R E rely on knowing that transconductance parameter. So this should be your first step. So our transconductance parameter is solved for quite simply as our collector current over our thermal voltage. So 5 milliamps over 25 millivolts. Careful of your units here. I've got them both in millivolts, so the millivolt terms will cancel, but we should have them in units of amps and volts. This gives us a transconductance parameter of 0.2 Siemens, or 200 millisiemens. Okay, now that we have our transconductance parameter, we can calculate the intrinsic emitter resistance. So we know that that's simply equal to alpha over GM. So our common base gain over GM we can calculate that common base gain as we've looked at previously as our common emitter gain over our common emitter gain plus 1. In this case, this ends up being 200 over 201. So our beta value is large enough that we can pretty well treat alpha as being approximately equal to 1. So this means our RE is therefore equal to 5 ohms. Okay, so bit of a sanity check of your answers here. We should expect this intrinsic emitter resistance to always be quite low. Okay, we looked at for currents of 1 milliamp that it was 25 ohms. Here we have currents of 5 milliamps, it's 5 ohms. But if you're getting values in the kilo ohms, you should be questioning what you're doing. Okay, finally we can calculate our pi here, knowing that our pi is simply equal to beta over our transconductance parameter, which is 200 over 0.2, and for our pi is equal to 1 kilo ohm. We could have also calculated our pi as beta plus 1 times RE, or 201 times 5 ohms, and you'll see that this is approximately 1K here again. We have a little bit of error here because we approximated our value of alpha up above. Okay, finally, recall back some time ago that we showed that we can calculate the output resistance. It's a function of the early voltage as our early voltage divided by our collector current, our collector current at our DC bias. So our early voltage is 100 volts divided by 5 milliamps. Be careful to put this in amps here so we get our units right. So my output resistance is 20 kilo ohms here.